Hey everybody, Mr. Stewart here. This video is being cast as a follow-up to the work that you began in class today. So it's a good opportunity to check some of your work. We won't see all of those solutions coming up in this particular video because I want to present some other information. We can actually take up some of the rest of the work tomorrow in class. So just so you can check your table quickly, you filled out the perimeter column. You identified that the pattern in the perimeter is that it is increasing by 4. Okay, so you can see that here as you're moving from one value to the next, we're seeing an increase of 4. That is, we're adding 4 each time. And interestingly enough, you identified in class, I noticed some people had also taken note that here with the values of the side length is that these were increasing by 1 each time all the way through. Okay. On the other side of the fence, when you were looking at area and side length, you were taking the squares of each of the sides. So in terms of squaring 1, you ended up with an area of 1, and squaring 2, an area of 4, and so on and so forth. Okay, the pattern within the areas, so you can see them increasing. So from 1 to 4, we see a positive 3 being added. 4 to 9, we're adding 5, and so on and so forth. Okay, the interesting thing this time is that we have a fourth column and that there is a pattern within the pattern. And you can see that we have consecutive increases in that first pattern of 2. Okay, and also take note that as the values of the side length increase, they too once again are increasing by adding 1 each time. Okay, so that's important to remember when we take a look at the graphs. So let's go there now. So you graphed by hand, and based on what you bring into class tomorrow, it'll give me a good opportunity to see how you're communicating your ability to graph. And I did this with an app online referred to as Desmos. Okay, so you can use it on your computer at desmos.com, or you can download the app to your smartphone and use it there. Okay, so here's what my graph looks like. Okay, so notice that I just have the ordered pairs being labeled. So for instance, 1 comma 4, which you can see here, 2 comma 8, and so on and so forth. Okay, and that one's here. On your graphs, you most likely joined the points with a line, and in that case, that is a good idea. Okay, so let me do that as well. Just going to find a line tool, and we'll place that line on here. Okay, and that line can continue indefinitely. Okay, just because of the fact that we happen to stop counting squares around 26, but it doesn't mean that it can't continue onwards. So I'm just going to put an arrow on the end of the line to indicate that it continues indefinitely. Okay. The reason why we can join points with a solid line, okay, notice that it is solid, okay, is that the values that we're using or can use, okay, are what we call continuous values. Okay, so I'm just going to write that there. So a solid line, that implies that the data is, or in this case can be, continuous. Okay. Okay. So what that means is that it's just not a solid line, but that means that we could use any values for side length. Okay, any values for side length. So we could have, if we wanted to, we could have been more precise. We could have started using decimal values, like 1.1, and had increased it that way indefinitely. Okay, so when someone asks you to use continuous values, that means that you're using all real numbers, okay, all decimals, fractions, anything like that. That's fair game. So it's not just whole numbers. So let's put that up here. That's probably a good way to say it. So we're not just using what we call discrete values or discrete numbers. Okay, I'll just put in or whole number values. Okay, we'll come back to that off and on over the semester. So if you're not using continuous values, okay, and only discrete values, you would not join the points with a solid line. Okay, but we'll come back to that later on. In terms of your values, you had found the differences. Okay, so from here to here, we're adding 4. This you had already done. Okay, what we can call that, there's several things we can call it. Okay, symbolically, we can refer to that as delta y. Okay, and the symbol delta, let's just go over here to the notepad. Delta, that means difference. Okay, to subtract or a change, right? What's the change in the y values? Well, they're going up by 4. Okay, we can also do that over here. Okay, I'm just going to, for example, because I'm running out of space at the top, delta x. Okay, and in this example, you can see that they're going up from here to here. That's a change of positive decimal 1. Okay, same thing here, a change of positive decimal 1. Okay, so that's the change in x, or delta x. Okay, so delta y, this is sometimes called the first difference. Okay, in y, and delta x is the first difference, okay, or change in x. Okay, so there's a little bit of background on how to interpret tables of values, names that you can assign to some of these patterns that you are identifying, and some names or terms that you can give to some of the information that's being held within the graph, which is very important as far as communication is concerned. Okay. Something else that you might want to take note of is look at where the graph begins. Okay, so it's starting here. It's starting at x equals 1. Okay, and the reason for that is that here you can tell that your table starts at an x value of 1. So in fact, this graph, okay, is being created for all values of x that are bigger than or equal to 1. Okay, and this is what we call a restriction. Okay, and typically restrictions are what we use when we want to specify what happens with x, or 2x, which is our side length in this case. Okay. So the way we use our x's will determine where the graph ends up, okay, or what the y values are, and will ultimately affect the shape of the graph. So there we have perimeter. Okay, let's speed things up a little bit here. So for this graph, okay, again, we're using continuous values. We're starting at 1 because we don't have a side length of 0. I guess we could have gone in between 0 and 1, but the table doesn't specify that. And this time, instead of a linear relationship, okay, we have a nonlinear relationship, which could continue indefinitely if we were using larger values for the side length. So this is a nonlinear relationship. Okay. So if we take a look here at the table of values, delta x1, okay, so you can see all the way through, we have that change of +1. Okay, and normally you wouldn't draw the arrows in the table. I'm simply doing that as an just to describe what's going on, okay, or at least to point out where I want you to look. The first difference, okay, delta y, okay, we have that increase of 3, 5, 7, 9, and so on and so forth. Okay, the pattern within the pattern, okay, we'll just refer to it now as the second differences. There is a symbol for that. We can grab that later on if we spend more time on this. And we identify those as 2's. Okay. So when you have a scenario where you have a constant second difference for a constant first difference in your x values, we refer to that as a quadratic relationship. Okay, so a quadratic relationship. More notes to come on this towards the end of the video. Okay, and the graph, in terms of its shape, we refer to this as a parabola. Okay, so there's a little bit of information for you in terms of this specific type of nonlinear relationship called a quadratic relationship. All right, well, let's move forward a little bit more. If more information comes available, we can always backtrack to the slide before. So this particular part of the video goes a little bit beyond the graphing that you did, because I want to introduce a term or two, okay, that would help you out in the future. So let's just say, for instance, that we wanted to use, okay, not in the context of area, perimeter, squares, or anything of that, but let's say we wanted to backtrack and start using negative values. Okay, let's just say that we wanted to do that. So in moving backwards, so the graph would intersect at 0. And then you would use symmetry to reflect each of these points through the y-axis. So I'm just going to do a few. We won't do them all at this point in time, but we'll just do a few here. Okay. And let's do one more for good measure. Right around here, that should be okay. I'll just grab a different color other than the red, and I'll continue this continuous curve. Let's just say it could continue on in either direction if we want to use all values on the number line. That is on this particular number line right here, which is x, okay, the x-axis. So notice that there's some symmetry here, okay, and that's a characteristic of all quadratic relationships. Okay, so this line here, this is what we call an axis of symmetry. Okay, so it's the vertical line about which you can reflect one side of the graph to produce the other one, which is the one I just drew over here. Okay, the axis of symmetry. This here, notice in this case, this point here is at the bottom of the curve. So this is a minimum. And in this case, this minimum happens to be the turning point of the graph. So we can call that a turning point. Or, okay, a vertex. You've used the word vertex in relation to where two line segments meet or two sides meet in a shape. It's also used here to indicate the turning point of this shape called a parabola. Okay, so again, the shape of this we refer to as a parabola. Okay. Notice also that the point 0, 0, okay, at this point we have an intersection with not only the y, but with the x-axis. Okay, when that happens, what we call that value, okay, so the value of x for the intersection is called a 0. Okay, not because specifically the number 0, there's more to come on that topic, but that intersection point with the x-axis for any graph, not just quadratics, is called a 0. Okay, so those are just a few bits of information that I want to bring your way, which is going to really help us to communicate our understanding as we move through the different forms of mathematics in our course. So let's take a look at what's next. Okay, and what's next, we're running about 16 minutes. I typically try to keep things between 15 and 20 if possible. So in this part, I'm just giving you some notes for you to jot down. So feel free to pause and rewind or just stop and take some notes. What you might want to do too is that if I give you more information here in the note, a really good practice, okay, in terms of helping to remember information is to go back into the notes, to the graphs, to the tables, and if there are any labels missing, add some of that information to your tables and your graphs. And I think you'll find that helpful in terms of memorization. So I'm just going to kind of read things out quickly here, and you pause and jot down things as you need to. Okay. So for linear relations, the graph is a line. In the table of values, you probably noticed that there was a constant first difference, okay, a constant first difference in the y values. What's really important too is that you have to see this too. You need to be able to take note of a constant first difference in x. If you don't have that, then you will not have a line. You'll have something that looks close to being a line, but you won't have a very strong correlation. That is, the line will not go through all points. There are two forms for the equation of a line, and that you would have labeled or answered in the lesson package. So the equation, there's two of them, y equals mx. That's what we call a direct variation as it passes through the origin. Y equals mx plus b. Notice this added quantity. The b is what we call a constant, which is just a number, okay, like any number added on. And that represents a partial variation. Okay, so the graph will pass through the y-axis at a value other than 0. Okay, and the m is the slope of the line. So remember that in a graph, okay, slope is seen as the ratio of rise over the run. So if this is my line going in both directions, between any 2 points on the line, we can measure the run, and perpendicular to the run, we have the rise. Okay. And one more little bit of information here on lines. In the table of values, okay, you can see it as a ratio, okay, of the first differences. So delta y divided by delta x. Okay, I'm just going to run this back for a second here. I think this is important as we approach the last minute here of the video. Let's take a look at the linear relationship. There it is here. Okay, notice your delta y's, positive 4, and the delta x is over here. This is all increasing by 1 each time, and that's the change in x. Okay, so in this case, you can see that the slope of the line, or rise over run, is 4 over 1. So delta y over delta x is 4 over 1. So either way, you can read the graph or you can read the table and it will give you your slope. All right, let's finish this up here. Okay, and last but not least, here's some information. I'm not going to read this out, but here's the name of the graph. Here's what you'll see in a table of values. And as far as equations are concerned, there are 3 different equations. And with the line, we had 2. In fact, there actually are 3 in the line, but we'll get to that later on. There are 3 forms, okay, of equation for a quadratic. So what you need to recall now or know is that the basic function or the basic equation is that of y equals x squared, which you would have determined in this activity. Okay, and there's some information here at the bottom about degree. That's a new term. It's just a way, when we do higher mathematics, when you have exponents that are getting larger and larger, it just makes it easier to describe the equations with the term degree. Okay, so we'll try to review this a bit tomorrow. Maybe we can do a Kahoot perhaps. So if you have your smart device, bring that with you. But otherwise, make sure you do take some good notes to this, and we'll continue tomorrow in class. See you tomorrow.